Hello everyone, I'm Yun Jia from Wisconsin-Madison. I'm presenting our work, Simple Adaptive Query Processing versus Learned Query Optimizers, Observations and Analysis. This work was in collaboration with Yanis Jignesh, who is currently at CMU, and with Theo, who is currently at Apple. Query optimizers in a database system is performance critical. It takes declarative SQL queries as input and predicts an optimized, efficient query plan. Within a query optimizer, it usually defines a search space of the query plans, and for the plans it searches, the query optimizer uses a cost model to predict the estimated final cost of the query plan. And finally, output a plan with a minimum estimated cost. However, such estimation can be not always accurate, because the traditional query optimizer usually uses oversimplified assumptions, such as independence among data columns. Given such inaccuracy, the predicted plan by the query optimizer could actually be very slow, and the optimal plan should be another plan instead. To address such inaccurate estimation, multiple works propose to use machine learning models to capture data correlations and improve the cost estimation. From previous results, it seems that the machine learning models can improve the plan cost estimation quality. There are multiple well-performing query optimizer based on machine learning, reinforcement learning specifically, such as NEAL, BAO, BAOSA, etc. However, from the system developer's perspective, machine learning-based optimization has multiple challenges that the developer need to consider when applying to a real system. For example, the machine learning models are hard to interpret, making it hard to understand a query performance. However, providing query performance is always important for users. Then, the machine learning model may not be able to generalize to unseen queries, making it hard to be applied to the scenario when the workload is changing frequently. It also engages a very expensive training or retraining step. In addition to the choice of using machine learning models, another alternative is to use adaptive query processing approach. Instead of using pre-trained models to capture data correlation, adaptive approach uses accurate runtime statistics to optimize the execution on the fly. Thus, it is fully interpretable, and there is no expensive training or retraining step required. Given such challenges of machine learning-based query optimizers, we currently see no commercial database systems that actually deploy the learned query optimizers, but we already see multiple systems that apply adaptive processing techniques already. So in this paper, we wanted to first analyze the learned query optimizers, and then compare the state-of-the-art learned query optimizers with simple adaptive processing techniques, and see how the adaptive approaches perform. To analyze the learned query optimizers, we answered two questions. The first one is, where does the improvement actually come from? To optimize the query plan, the query optimizers need to do two orthogonal optimization decisions: join order and physical operators. Since these two both contribute to the final performance, probably improved performance, it would be interesting to understand which decision makes more contribution. By doing this study, we can know whether it is learning complex join orders or simply tuning the physical operations. In this study, we use BAOSA, which is a state-of-the-art learned query optimizer, to conduct the study. We use four configurations as follows. The first two are BAOSA overfit and BAOSA overfit join order. In these two configurations, all queries are treated as training queries. And in BAOSA overfit join order, we only use the model to predict the join orders. The other two are normal BAOSA and BAOSA join order. And in BAOSA join order, we only use BAOSA to predict the join order. In this experiment setting, if BAOSA performs similar to BAOSA join order, then we can say that the join order contributes more to the final performance improvement. Here are the results of Postgres and corresponding BAOSA performance. The blue bar represents the performance of Postgres. The height of the bar represents the average runtime, and the standard error are also reported. From this figure, we find that performance of BAOSA overfit is similar to BAOSA overfit join order, which means that the performance improvement is mainly from the joint order. And for BASA joint order and BASA, although the average performance differences between them are larger, but the standard errors still overlap with each other, showing that the difference of these two are not statistically significant. Thus, we can make the conclusion that the joint order plays a more significant role in the performance improvement. Next, since the machine learning models are typically trained on a relatively small set of queries, we think that the performance of machine learning model can vary a lot when the workload pattern changes. Therefore, to verify this guess, we analyzed the learned query optimizer to study the generalizability, that is to say, studying BASA's performance on totally unseen queries. To this end, we create a split of the query in the joint benchmark into 6 groups. Each group has queries with different number of joins. Group 1 are the queries with the least number of joins, while Group 6 contains queries with the most number of joins. To study generalizability of learned query optimizer, we perform a cross-validation with a 6th group of queries. For example, BASA is first trained on Group 2 to Group 6 and tested on Group 1, because Group 2 to Group 6 have the queries with a different number of joins than queries in Group 1. In this case, the performance of BASA on Group 1 represents the generalizability. This figure shows the results. For all groups of queries, BASA cannot provide better performance than Postgres. This actually verified our guess that BASA is not able to optimize performance of Postgres when faced with completely unseen queries. This finding is not super surprising for us, but this verifies the significant challenge that learned query optimizer actually have. The challenges of learned query optimizer make us rethink how these two dimensions can be optimized with adaptive query processing, given the multiple benefits that adaptive query processing has. As for the two joint order selection and physical operator selection, we choose two very simple adaptive processing techniques that directly optimizes these two dimensions. For the joint order selection, we use look-ahead information passing, which is also called LIP. What LIP does is to push down the selection predicate in the query processing pipeline to reduce the number of rows passed as unnecessary intermediate results. For example, in this query plan, there are 4 selection predicates, sigma 1 through 4. Sigma 3 and sigma 4 are 2 predicates in the later phase of query plan. For these 2 predicates, LIP first builds Bloom filter by adding the keys that passes the predicate. Then the Bloom filters are further passed down in the query processing pipeline to the bottom of the query plan for popping as a new predicate. If there are multiple Bloom filters at the same level, the Bloom filters are reordered based on the selectivity. The Bloom filter that prunes more rows are pulled up to the front, making as fewer filters propped as possible. LIP is not a new approach, but it has been approved to be very effective in multiple scenarios, making the query not sensitive to joint order anymore. For more information, you may refer to the following paper. LIP has been applied to a new version of SQLite, showing the real-life applicability of LIP. The other approach to optimize joint algorithm is to use adaptive joint algorithm to dynamically choose the joint algorithm during execution. With adaptive joint algorithm, all joins in the query plan are executed with adaptive join. The procedure of such algorithm is also very simple. It starts with building a hash table by default and choose from 3 join algorithms based on the size of hash table. If the size of hash table is smaller than a threshold and index is available on the inner loop, it considers using index nested loop join. If the size of hash table is smaller than another threshold, the index is not available on the inner loop, it's going to consider using simple nested loop join. Otherwise, if the size of hash table is large, it continues the hash join. Like LIP, the adaptive join algorithm is also not new. It is already applied in SQL Server for many years. The reason why we choose LIP and adaptive join algorithm is twofold. First, like optimizers, no matter learned optimizers or not, These two adaptive query processing techniques optimize the performance along the two commonly used dimensions, join order and physical operators. Secondly, they are all very simple techniques, but have been applied to modern commercial systems. By comparing the state-of-the-art learned query optimizer with these two techniques, we can show how commonly used adaptive approaches can compare with modern learned query optimizers. As we also use Postgres as the testbed, we next going to introduce how lib and adaptive join algorithm are implemented. As for lib, we implement it as a Postgres extension. There are actually two phases of lib, Bloom filter building and probing. We implement the Bloom filter building and probing with multiple extended C functions and rewrite the original query. First, for the predicate that can be pushed down in the pipeline, we use C functions in the lib extension to build the Bloom filters. In this Bloom filter building block, lib scans the input tables and add the corresponding keys to the Bloom filter. Then the Bloom filters are used to be probed in the query. This implementation provides us a simple proof of concept implementation of lib without touching the core code of Postgres. As for adaptive join algorithm, we determine the two threshold with a simple grid search. We create a simple query template with a variable n to change the size of hash table. As we change n, we show the cost of the two flavors of nested loop joins compared to hash join and derive the threshold. In the first figure, we compare the runtime cost of hash join versus index nested loop join as we increase n. We derive a threshold of 500,000 in this case. Similarly, we have a threshold of 1 for the non-index version, that is to say the simple nested loop join versus hash join. Then we simulate the adaptive join algorithm by first executing the query with hash join. Then according to the true size of the hash table, we manually apply the adaptive join algorithm and specify the final algorithm using PG hint plan. Here are the evaluation results. We compare the adaptive approach with two learned optimizers, Balsa and Bao. We followed a similar setup as Balsa and test the performance on two train test splits, drop rand and drop slow. In drop rand, we randomly select 19 queries as the test queries, and the remaining queries in drop are treated as training queries for Balsa and Bao. As for drop slow, we select the top 19 slowest queries in Postgres as the test queries, and learned query optimizers are trained on the remaining fast queries. On drop rand, our adaptive approach, lib plus AJA, provides similar performance as the learned query optimizers, while on slow queries, lib plus AJA performs even better than both Balsa and Bao. We also apply the adaptive approach to the plan generated by the learned query optimizers. The solid red bar represents the original Balsa, and the shaded red bar represent after applying the lib plus AJA on the plans generated by Balsa, same as the sign bars. The results show that adaptive processing can improve the query plan generated by learned query optimizers by reducing the average runtime, and it also provides robustness by reducing the standard error. We also apply lib to a set of complex query constructs such as subqueries, and CTEs. We create a workload called TPCH complex by selecting some of the queries in TPCH workload that contains such complex query constructs. Our results show that lib can also work on that, which are currently hard for learned query optimizers to handle. To sum up, in terms of query performance, adaptive processing with lib plus AJA provides a similarly good performance as learned query optimizers, but it also provides better performance in many cases, such as better performance on slow queries and more robust to workload changes. As for generalization, since adaptive processing is intrinsically not overfitting to any workload, it has better generalization compared to learned query optimizers. Also, adaptive processing does not require any training or retraining steps. The cost of building such method is better than learned query optimizers. In addition, it also works on complex query constructs, which are currently hard for learned query optimizers to handle. Therefore, going forward, Future learned query optimizers may need to compare with a simple adaptive query processing technique. Thank you.